Welcome to the Crazy Hat Chemist. So another video here on electrochemistry. So let's get moving. Bam! So today we are talking about the steps of balancing redox reactions. Remember, that's reduction oxidation reactions. So I'm going to go through these here really quick here for you, and then we are going to follow these steps on doing our first balancing equation. And we have a little joke at the end of this, so don't forget to hang on to the end of this video. I got a cool chemistry joke here for you. So number one, we're going to assign oxidation numbers to all the elements. That's critical. And if you don't know how to do that, watch the previous video that I just made. Number two, we're going to divide into two half reactions. One reaction for oxidation, one reaction for reduction. Okay? Number three, we're going to balance for mass, that is, we're going to balance the atoms for mass, except for oxygen and except for hydrogen. Okay, number four, we're going to balance oxygen atoms by doing the following. We're going to add one water for each unbalanced oxygen. Okay, number five, if necessary, we're going to balance the hydrogens and we're going to add hydrogen ions as needed. And if you're going to have an excess of hydrogen ions, then it will be an acid solution. So if you are balancing an equation within acid, if it says that, then you're going to be at least coming up to this point, skipping the next point. Number six, if in a basic solution, you're going to add hydroxide ions to both sides, this is critical, to both sides, to equal or the equivalent number of hydrogen ions that I had added earlier in step number 5. And remember that one hydrogen ion plus a hydroxide ion is equal to one HOH, which is an H2O water. That's critical. Okay, number 7. We're going to balance for charge in each half reaction by adding electrons. You never subtract electrons, you only add electrons. Number 8, we're going to multiply by a factor to cancel out the electrons in both half reactions. So you need to multiply both the oxidation half reaction and the reduction half reaction by a whole number, like stoichiometric whole number. Okay, number 9, we're going to add the half reactions, canceling the electrons so that when I sum up the two half reactions, there are no net electrons in the equation. Okay, this is actually the whole premise of this balancing reactions, redox reactions, using this method. So the reason that we use this method is that we want to cancel out the electrons. That is really the end goal. Once we have canceled out the electrons, then we will have a balanced equation. Number 10, you're going to simplify. There might be waters on both the reactant and product side. Okay, you need to check and you need to label, i.e. you're going to label which one's oxidation, which one's reduction. Where's the reducing agent? Where's the oxidizing agent? Where's the cathode? Where's the anode? All these things need to be labeled based on this balancing of the equation. Okay, make sure you look at that previous video of assigning oxidation numbers, because without assigning oxidation numbers, we can't balance a redox reaction, period. All right. So let's do our first example. Remember, there's a joke at the end. Okay, so here's our first balancing electrochemical equations number 1. Okay, we're going to balance the redox equation when copper wire is added to a solution of silver nitrate. Okay, now this is a very famous reaction here, and this is what I would call a Christmas tree reaction. So always during that December time frame, I take some copper wire, form it into a tree-like form, then from that tree pyramidal form, then I add a solution of silver nitrate, which is colorless. Over time, what happens, this is a spontaneous reaction. Over time, a blue solution appears and you will see a silver Christmas tree. So that's when the silver Christmas tree appears. Okay, so a blue solution is actually giving you a hint as to what oxidation number copper is going to be in. Okay, so we first need to write the reactants, figure out what type of reaction it is, then write the products, and then we can balance the equation by dividing it into two half reactions. So let's give that a try here. Okay, so, well, I'm going to repeat just key parts of this. It says copper wire. So copper is an element in its standard state as a wire that's a solid. So it's just Cu that's a solid. Okay, and a solution, that means it's aqueous, of silver nitrate. Silver is a periodic trend charge of a 1 plus. Okay, that's right there as a 1 plus, 2 plus, and aluminum is a 3 plus off the chart there. So silver is a 1 plus. Nitrate is a polyatomic ion that's NO3 with a 1 minus charge. I'm going to take the silver 1 plus and the nitrate with a 1 minus, flip the charges, bring it down, or balance the charges, and I get silver nitrate aqueous. So this is my reactant side, which is copper, which is solid. Okay, it's an element in its standard state, and then silver nitrate, that's AgNO3, aqueous. Now we need to figure out what type of reaction this is. I have an element on the reactant side and a California that is a compound that's a cation-anion combination. So that lets me know that this is a single displacement or single replacement type of reaction. Okay? From that, you should recognize that silver, okay, and copper, those are the two metals that form cations. Now, copper is higher up on the activity series than silver is. So therefore, this is a spontaneous reaction. So what you do need to do is you need to look at an activity series, and that activity series will let us know whether this reaction will be spontaneous and occur and you get products, or non-spontaneous and you don't write any products. It just so happens that copper is higher up than silver on the activity series. Therefore, the copper is going to displace the silver, and the copper now will combine with the nitrate. The silver will be an element all by itself, and that is what you get right here on the product side. You get silver that's a solid in its elemental state, and you get copper 2 nitrate. Okay, again, that blue solution appears, lets us know that it is copper 2 plus. The blue solution is characteristic of a 2 plus copper ion. So now what we need to do here is follow the rules that we aforementioned in the previous, in this video at the beginning of this. And I noticed I already put this in there, but I already said it there, and that's copper 2 plus is that blue characteristic solution color. Okay, so what we need to do now is label each of these elements, and we need to label them with their oxidation numbers. So because copper is in a solid in its standard state, it is a 0. Okay, its oxidation number is 0. Remember, elements in their standard state are 0. Copper is a metal, it's a 0 charge. Okay, that silver is a +1, and that's how I obtained the formula of silver nitrate, and so I know that the silver is a +1. Now, the oxygen is a -2, and if you follow the previous videos in determining oxidation numbers, we determined the oxidation number for nitrogen in a nitrate ion, and it was a +5. Oxide ion is a 2-. Then on the product side, we have silver. Okay, silver, that's an element by itself, so therefore it's a 0 charge. It's not a cation, it is not combined with another element or polyatomic ion, therefore it's an element by itself. Okay, and then the copper charge is, of course, the characteristic blue color, and that is the 2 plus. Now, the NO3 is a polyatomic ion nitrate, just like it was on the reactant side. So therefore, you should understand, if you got the nitrogen's charge on the nitrate, you should be able to get the nitrogen's charge on the nitrate on the product side, and the reactant side is the same. So that's why that nitrogen is a +5, and of course the oxygen is a -2, because it is not an element by itself, that's diatomic oxygen, and it is not a peroxide or with fluorine. So now what you need to do, now that you have the reactants and the products, now you have labeled all the oxidation numbers for all the elements. Once you have labeled all the oxidation numbers for all the elements, now you need to look at the reactant side and the product side. Okay, and now you need to figure out what elements, there will be 2 of them, probably, most likely, not in every case, but most likely there'll be 2 elements that will change in oxidation number. From the reactant side to the product side. So the reactant side of the copper is a 0. The product side of a copper is a 2+ charge. That lets you know it's going from a 0 to a 2+. The other change that's occurring is the silver on the reactant side is a 1+, and on the product side it's a 0. So this means that I'm going to combine the two coppers and their charges, and I'm going to have a 0 charge on the reactant side going to the +2 on the product side, and that's an increase in oxidation number. Since that increase in oxidation number is characteristic of oxidation, I have just labeled this as an oxidation half reaction, if you will. Okay, the silver that's going from a 1+ to a 0, that's a decrease in oxidation number, and that of course is a reduction. Okay, if you have oxidation, you must have reduction. If you have reduction, you must have oxidation. Now what we're going to do is we're going to write out just the oxidation reduction half reactions. There's 2 half reactions. So we're going to do those and pull those out of this entire equation. So this is the oxidation half reaction. This is the reduction half reaction. Notice that what I've done here is I've kept my arrows right in a line here with the oxidation half reaction and the reduction half reaction. Now we're going to follow those rules that I aforementioned in this same video. Okay, we're going to balance the atoms that are non-oxygens and non-hydrogens first. There's 1 copper on the reactant side, 1 copper on the product side, so they're balanced. 1 silver on the reactant side, 1 silver on the product side, they're balanced. I don't have oxygens or hydrogens to deal with, so I can skip all of those steps. Now what I need to do is balance for charge. Balancing for charge is by adding electrons. So with the copper oxidation half reaction, you should see that the reactant side has a 0 charge, the product side has a +2 charge. So I need to add to have both sides equal the same charge. And you're always going to the lower charge. Think about it this way. You have a 0 and a +2. What's lower? 0. So I'm going to always go towards the lower of the 2 charges from the reactant to product side. It doesn't really matter. So I'm going to add electrons to the product side so that the product side's charge is equal to the lower charge of the reactant side in this case. And so I'm going to add 2 electrons. This will make the product side equal to a 0 as the reactant side is already equal to a 0. Okay, now the reduction half reaction. The reduction half reaction, I have a +1 charge on the reactant side and a 0 charge on the product side. So what is the lower charge of a +1 and a 0? Well, it's 0. Not always 0, but it is in this case. It's a 0 on the product side, so I need both sides to equal 0. So how do I do that? Adding electrons. Never subtracting, but adding electrons. So how many electrons do I need to add to the reactant side of the reduction half reaction with the silver in it? I'm going to add 1 electron, because 1 electron plus the 1 charge, that equals a charge of 0. That's the lower of the 2 charges on both the reactant and product side. So now what I have done, I've effectively balanced the charges, okay, by adding electrons. Now I need to make sure that when I add up the oxidation half reaction and the reduction half reaction, that the electrons cancel out, okay? So I'm going to multiply both equations by a number. I'm going to multiply the oxidation, the copper half reaction, by a 1. I'm going to multiply the bottom reduction half reaction by a 2. So now I'm going to distribute that 2 over all the terms in that reduction half reaction. And then I get the following. The copper half reaction, that's an oxidation half reaction, does not change, okay? But the reduction half reaction with the silver does change. I should have the 2 electrons, 2 silver ions, and 2 silver metals themselves with no charge. Now I'm going to draw a line in the sand, and I'm going to add these 2 half reactions up. Before I add these 2 half reactions, the key to solving this is that the electrons cancel out. In order for the electrons to cancel out, you need to have the same number of electrons on the reactant side and the product side. That will allow the electrons to cancel out. Then you can bring everything down. Now, what we're going to do is distribute those coefficients as is appropriate. So, copper that has a 0 charge has a coefficient of 1. Silver that's a 1+ ion has a coefficient of a 2. Silver that's a solid metal with no charge has a coefficient of a 2. Copper ion that's a 2+ charge has a coefficient of a 1. So I'm going to place those on that original equation there, and then I get the final balanced equation. Bam! That is my final balanced equation here. I have 1 stoichiometric coefficient on the copper, 2 silver nitrates yields 2 silvers plus 1 copper nitrate. Now, the last thing that you're going to do is you're going to make sure that you've got the correct answer, and you're going to label things. Okay, and so you're going to make sure that you're going to check everything. So that is on the reactant side, there's 1 copper. On the product side, there's 1 copper. On the reactant side, there's 2 silvers. On the product side, there's 2 silvers. On the reactant side, there are 6 nitrogens. On the product side, there are 2 nitrogens on the reactant side. On the product side, there are 2 nitrogens. On the reactant side, there are 6 oxygens. On the product side, there are 6 oxygens. Now you have effectively balanced this equation. Okay, now we're going to do some labeling. This is the oxidation, and this is the reduction. You always label the reactant side when labeling oxidation, reduction, oxidizing agent, reducing agent. You always label the reactant side. Okay. The other thing that I want to mention here is that this is the basic equation of balancing electrochemical oxidation reduction reactions. You could have balanced this equation without using this method here. And you could have looked at that white equation that I had originally with the oxidation numbers labeled on it and go, there's 2 nitrates. I'm going to put a 2 in front of the silver nitrate. Now I'm going to put a 2 in front of the silver. Done. And you would have been done. But I'm trying to show you the process and how to do it with this method here. And if you know how to use it with this method, we'll be able to do more complicated problems, especially when they're in acid and base. You won't be able to balance them by inspection via other methods. Here's a little bit of physical fitness humor. So we are combining our chemistry and our PE courses together. And that is, if a chemist becomes flabby, what do you do? Well, you fermium up. You fermium, right? All right. So I am the crazy hat chemist, and of course I can't end this without a crazy hat, and I've got myself a pizza hat, okay? Man, it's about lunchtime right now, and I'm getting a little bit hungry. I'm hoping that you enjoyed this video. Hopefully you learned how to balance redox reactions very simply, a simple one. We're going to get into some more complicated ones. If you like this one, give me a thumbs up on that video. If you like this one, then please subscribe to my YouTube channel. I got lots of awesome videos. And if you know of anybody else that needs chemistry help, then please have them subscribe to my YouTube channel as well and pass it on to all your friends. In your chemistry class, pass it on to all your friends. You can actually find me on the World Wide Web, or Google me, and you can find my website. On there, you can get a cool sticker that my son designed, as well as a cool t-shirt with my logo on the front and my website on the back. I hope you have a fantastic day. I will see you next time for more balancing of electrochemical reactions. We have a lot of these to do, as you can see from that slide right there. I'll see you next time. Bye for now.